Okay, cool. So what did we do last time? Last time we did a little bit of like, we just kind of finished off talking about some convex MPC examples, right? Convex MPC is awesome. And what else we did? Then we went into sort of nonlinear trajectory optimization. And then we talked about DDP and ILQR. Kind of got through just through the derivation of that, right, last time. So today we're going to pick up on that and kind of go into some more details and sort of extensions, and also do lots of code demos because they're fun. So sort of DDP details and kind of extensions, specifically things like handling constraints and free final time, minimum time problems, things like that. So which show up in a lot of applications.
Is the vectric like the main way that you solve those tensor terms?
Yeah, I mean, that's how I do it. That's how I do it for sure. That is, I mean, there's like, 3 or 4 completely equivalent ways to write those things. At the end of the day, the actual operations on your computer are all the same, right? No matter how you write it, they end up being these like, lots of vector, matrix, tensor, multiplication type things. And like, doesn't really matter a ton how you write it down, as long as you implement it correctly. I find that the vectric stuff is kind of the easiest way to write it down personally, but there's no wrong way as long as you get the answer right.
Yeah, and you said it was analogous to the Gauss-Newton method last time. Is that like, does that mean that you don't use it that much in practice in favor of ILQR?
Yeah, so I would say like probably 90% of implementations, and in 90% of situations, people just do ILQR and leave out those extra terms. And so just do Gauss-Newton. That is the common thing. And we'll talk more about that today. Does anybody have any questions about anything from last time? No? Good. Okay, cool. So as a quick recap, just going to write down kind of the DDP thing again, since we were very sort of in the weeds last time in deriving it. And just to kind of like summarize, DDP is a method for solving kind of the following, we'll call it unconstrained trajectory optimization problem. So it looks like this, right? We're doing min over our state trajectory and our control trajectory of the sort of standard additive cost. So we got a stage cost and a terminal cost, subject to just the dynamics. And sort of one way of thinking about the whole like DDP ILQR thing is it's a very efficient sort of, you can think of it really as just an efficient sparse matrix sort of technique for solving this specific problem, which has some really specific structure to it, right? Okay, so we have the problem, and then the kind of the first piece that we did last time was the backward pass, which is basically ricotti. Basically the same thing you see in standard LQR, but with some extra terms. So that looks like we do this sort of value function or cost to go function approximation using a second order Taylor approximation. So we get something that looks like this. Right, and we start things off at time step n by just using the Taylor expansion of the terminal cost. So we get Pn equals the Hessian of the terminal cost. And we get little Pn, the gradient, gradient of the terminal cost. Cool. And then we do the standard Bellman recursion thing. So we do Vn minus 1 x plus delta x is min over delta u of the action value function of the second order Taylor expansion of the action value function, right? And we specifically, we're doing this over the deltas, sort of, we're minimizing that second order Taylor approximation. And last time we kind of derived all this out in terms of sort of this block matrix setup, right? Where we did the second order Taylor expansion of the action value function in terms of both x and u, got like this block matrix for the Hessian, the gradient, kind of massaged that around, and we got the following conditions for delta u. So delta u n minus 1 is going to be minus d n minus 1 minus, so that's the feed forward term, and then we got the feedback term on delta x. And then we sort of plug this back in to get our next big P. I guess I should write, these should be, if we're being general, these are Ks, not Ns for this recursion. And then Pk minus 1 is these Gs, which are the action value function Hessian blocks. This is the K we just solved for. So that's the Hessian term, and then the gradient term. Okay, that's the whole thing. And so once we do that, we've now bootstrapped ourselves and we've got the next time steps. And now we can do k minus 2 and just keep going all the way back until we get to time step 1, right? And then at that point, we've got the Ds and the Ks for all the time steps along the whole trajectory. And then we do the forward rollout with that step with a line search. So we do, we're going to sort of do the pseudocode thing. So this delta J is going to be our expected cost decrease according to the Taylor approximation that we're going to use in our NIHO. And I'm going to use primes for the new updated trajectory, just because I'm using subscripts already for the time steps and stuff. So we're going to say X prime, our new updated trajectory at time step 1 is equal to X1, our original initial state. So these are just the initial conditions, right? The current, the state at time 1. Then we're going to roll out from there. So for K equals, this is time step K, which is maybe, hopefully not ambiguous, 1 to n minus 1. We're going to do the new U, so U prime at time K is the old U, minus our alpha, which is our line search parameter, times the feed forward correction, the D, minus the feedback term. So this is our K, time step K, and it's the new X minus the old X, so the delta X, right? And then we plug this into the dynamics to get our next state, the updated one. And we also compute our cost correction. This is awkward. Okay, so that's the rollout. And we do this sort of line search thing, sort of around this, which is the standard Armijo thing that we've talked about before, just applied in this context. So we start with alpha equals 1, and we do the following thing. We do the rollout with alpha equals 1, and we get this new X and U trajectory and this expected cost decrease from that rollout. Then we sort of chop the step size down by some factor C, like before with Armijo. We do this while the Armijo condition isn't satisfied. So that would be, the new cost is greater than the old cost minus the some tolerance times the expected decrease. And then once that's Armijo condition satisfied, we set the nominal trajectory equal to the new updated one, and we repeat until we converge. And as you'll see in the code in a sec, the convergence tolerance we're going to use is the norm, some norm on the Ds, and then we're going to use the infinity norm, aka largest magnitude value is less than some tolerance. So what this is saying is the Ds, remember, are the feed forward corrections on the Us, and they're coming directly from they're basically the gradient of the cost to go with respect to the controls. So when those go to 0, it means you can't improve anymore by updating the controls, right? So basically go until that feed forward correction on the Us is small, with respect to some tolerance. And then we call it good. And we say we're not really moving anymore. We must be close to the optimum, right? Does that make sense, everybody? So any questions on this whole setup? Yeah.
So what part of this makes it a constrained trajectory optimization? Is it the dynamics are not here?
No, so when I said unconstrained, specifically what I mean is it's only that problem right there. There's no additional constraints like torque limits or keep outs or obstacle constraints on the state. So there's no state or input constraints in addition to the dynamics.
So it still can handle constraints.
That's right. Yeah, it's only can handle that exact problem formulation right there. So you have cost, additive cost function, and dynamics constraints. That is what it solves. If you do anything else, it breaks, right? So it basically, really what it's doing, like one way to think about this is it's iterative LQR. Like it's basically going to linearize that and turn it into an LQR problem and apply the LQR stuff to it, and then iteratively relinearize and resolve it using an LQR approximation. So just like LQR can't handle constraints, right? That's the way to think about it. Does that make sense, everybody? Anybody else have any questions? Cool. Okay. So let's see. I think it's time to do some stuff. So let's do some code stuff. That's what we talked about last time, right? Kind of the stock algorithm. Here's some code, and then we can talk about it. So you want to see that? Okay. All right. So let's see. First, we'll do a cart pull. Does anyone know what a cart pull is? Yeah. Anyone not know what a cart pull is? Cool. There'll be an animation in a second. So here we go. So this is coming from our dynamics library. So I didn't have to write this down by hand. 20 Hertz time steps. We're going to use RK4 like we've been doing. And I'm specifically here with this is I'm using 4diff, which is automatic differentiation, right? To get the A and B matrices. That's what these guys are, right? Derivative of the dynamics with respect to X and U. And then I'm also going to get the second derivatives of the dynamics by just nesting the 4diff calls. So this is like the derivative of the A matrix with respect to X with respect to U, B matrix, et cetera. So these are those tensor terms, right? That are kind of flattened out. And I'm using the vectric stuff that we talked about before, right? Cool. So that's that. This is sort of uninteresting stuff. So 5-second horizon. I don't think that's interesting at all. Cost function, quadratic cost that I made up. Yeah.
Numerically, is it bad to nest 4 diffs? or like numerical differentiation?
So numerical differentiation, absolutely. This is not numerical differentiation. This is automatic differentiation, which is a totally different thing. So this is exact. Yeah. So does everyone know how automatic differentiation works? Does anyone not know about this? Okay. So this is worth, yeah. Sorry. Didn't know. Yeah. Okay. So maybe this is worth it. So this is like the heart of modern like machine learning, like PyTorch and all these toolboxes. All they really are sophisticated automatic differentiation frameworks. What automatic differentiation means, so numerical differentiation, like finite differencing, is like I compute some delta, right? I evaluate the function at some delta, and then I divide by the delta, right? And I get some approximation. So that's noisy, and sort of nesting that is bad. There are good ways to do it, but it's not trivial. And that's always going to be sort of inexact and have round off error issues and all kind of stuff, right? Okay, so this is a different thing. This for diff thing and what things like packages like PyTorch do, they basically, they overload the numeric types in the language. So here, like instead of a double, I'm passing in like what's called a dual number type. And basically all that is a numerical, it's like a little type that you can define that's overloading the standard number type that has both the value and the derivative value in a little struct or class, right? And then what you do is overload all of the standard operators in your language. So like multiplication, division, addition, et cetera, and overload all of the functions you care about. So like all the trig functions, right? So all these functions that I use when I write down dynamics or any other type of function, I know all the derivatives of all of those little individual functions, right? Sines, cosines, whatever you want, like pick a standard function, right? So I overload all of the standard library of functions in my language that I care about with their derivatives as well. And I define those derivatives on these dual number types. And then I just implement the chain rule. And now basically when I go call a function on these dual number types, if I implement this kind of in the standard way, I'll get both the value and the derivative for essentially for free by just calling the function. And it's exact to machine precision. So literally all you're doing is writing down, implementing all the derivatives of all the functions, the base functions and the chain rule. And then it all just kind of magically works. It's pretty slick. It's kind of awesome. There's a bunch of cool things about this too. There's this really cool result called the cheap gradient theorem. Has anyone heard of this? It says that basically, to paraphrase, the cost of evaluating a gradient is a constant factor more expensive than evaluating the function itself. So essentially, like evaluating derivatives is almost free. It's only like some small amount more expensive than just the original function call if you do all this AD stuff correctly. This is why machine learning works, basically. This is why like all the deep learning stuff sort of is a thing now, because you can do this stuff really efficiently. Anyway, is that cool with everybody? It's worth a look. It's actually like surprisingly straightforward, and you can code it up yourself like surprisingly easily. It's worth a Wikipedia. It's cool. It's also one of the big ideas behind machine learning and why it works and stuff. Okay, so that's worth a look. Yeah, so in here, I can most of the packages will let you diff twice, double diff, but there are weird quirks often. Like you can double diff in PyTorch, but it has issues and it's sort of quirky and you have to be careful. So you can always do one derivative. You can usually do two derivatives with these toolboxes, but maybe some caveats. And you pretty much can't do more than that usually. Okay, stuff, cost function, same stuff we did before. Okay, I broke this out. So here's the backward pass that we just wrote down. Startup time step n with the gradient and Hessian of the cost. And I just wrote that by hand. And then this is exactly what we wrote down before, right? Start at the end, kind of evaluate my derivatives. And then I've got here, I have the ILQR, aka Gauss-Newton version, and the full Newton version with the tensor terms over here, where I wrote them down using the Cron-Vex stuff. So this com thing, that's the commutator transpose matrix thing, right? And that's all kind of it. So what I'm going to do, we're going to compare kind of the standard. We're going to compare full Newton and Gauss-Newton or ILQR DVP here. So I'm going to start out with just ILQR, just this stuff. We'll talk about this later. Initial guess is just like almost hanging down, in the, does anyone know why I put in some initial U that's pushing it to the right? I don't have any, why wouldn't I just put zeros? You don't have any thoughts on that? Yeah.
Hanging down as a stable point.
Yeah, but in principle, if I just threw zeros, all zeros, and let it sit there, like why? Anyone have any thoughts on why that would be a bad initialization for this? Yeah. Yeah. So it turns out, right? There's this problem's symmetric, right? And so going left or going right gives you the same cost, and so it's sort of like it's a weird flat spot at the bottom where you have this arbitrary choice of going left or right. So I put in a tiny torque to push it one way to basically break the symmetry so it like sort of has a good gradient in one direction and doesn't get stuck at that initial point, which is kind of weird. There's all kinds of weird little, quirks that you will find in doing this stuff. Initial rollout, evaluate the cost, or whatever. And then here's the rest of the algorithm. So backward pass, and then this is the rollout stuff we just talked about. We just wrote this down. And then this is my line search stuff. I have a little like extra little kind of checking stuff in here because there's situations where things can blow up on you. So I check for nans. Otherwise, it's exactly what we just wrote down, right? So there's that. Okay, so this is actually going to run now. And it looks like 691 iterations with standard LQR. It's basically instantaneous, right? And then here's the trajectory that comes out. That's the states, that's the controls. And like, let's go watch it and see what it looks like. Network not cooperating. Okay, we got to do this. There we go. Okay, so that sort of seems reasonable, right? Let's do it one more time because it's kind of fast. So it's just a little 5-second trajectory. I didn't put any torque limits on it or whatever, and it kind of figures out how to swing up. And then the goal is to get it upright and the cart at the origin, right? So that all worked out. Cool. So let's see. Super fast. It's up there quick. So remember this and this. So the cost it finds is 363 something, 691 iterations. I'm going to now go in and do the full DDP with the extra tensor terms, and let's see what that does. So here's all those second derivatives, which are kind of expensive to compute, like we talked about, and then stupid stuff. Okay, let's come at this stuff. Come at this stuff. All right, rerun. Oh, I need to kick it off. So I need to sort of get my initial guess in there again. Backward pass, initial guess, roll out, same stuff. This is going to be a lot slower just because those terms are expensive, but oh yeah, we need to talk about this too in a sec. And yeah, okay, so last time it was at 691. So this time 552. So it took less iterations, but as you noticed, right, in terms of wall clock time, a lot slower. That's mostly down to my bad implementation. Like if you were careful about implementing this, there are smarter ways to do this, right? My code's not great, like not optimized super well, but like it's always going to be slower. There's extra stuff in there. And in general, in terms of wall clock time, the Gauss-Newton thing pretty much always wins, and everyone pretty much just does that because the reduction in iteration count is like a little bit, but it's not huge, right? It's not orders of magnitude. This was maybe like what, I don't know, 20% less iterations, but the iterations are like several X more expensive. So it ends up wall clock time still losing. You basically find the same solution. So it's like same cost, same trajectory. Right? Didn't do anything different that way. Watch this again. Exactly the same, right? So that's not that cool. What else is there to say about that? Okay, the other thing I got to talk about is, I put this in here on purpose. So I have this regularization block where I check positive definiteness. So remember we did this in the sort of Newton versus Gauss-Newton story. We talked about this back at the beginning of the class. These tensor terms, so this whole thing, all these terms, right? This is the Hessian of my action value function, right? And that's the thing I'm minimizing as I go backward, right? So I need that Hessian to be positive definite to have a well-defined local minimum, which is what I'm trying to do. So I build that block matrix here kind of explicitly, and I check if it's positive definite. Again, this is not the most efficient way to do this. You shouldn't do it this way in practice. You should be a little smarter about this, but for educational purposes, that's what you want to do, right? And we need this to be positive definite. I'm doing the same sort of thing I did before, where I like pad this thing with a multiple of the identity. Here, what I'm actually doing is padding pk plus 1. Does that make sense to everybody? Everyone see that? So this is like, where this would have shown up added onto pk plus 1, right? Is what I did here to pad this up. And then I kind of do standard things. Notice when I did the ILQR, aka Gauss-Newton version, we never got these regularizing things, right? It didn't need to regularize, and that should be the case with Gauss-Newton. We'll talk a little bit more about this. You still might need a little bit because of numerical round-off stuff, but in general, with full Newton and with DDP, you're gonna have those tensor terms can make your Hessian indefinite. Like same story as when we did this for standard Newton optimization. So we have to regularize in general when we do this full DDP thing. So that's more complicated. That's about all there's to say about this. Any other questions about this? Is this cool with everybody? So save a few iterations, need to regularize, generally not worth it, is sort of the full story. Some problems might be worth it. Okay, so that's the carpool. Now we're gonna look at some other stuff. This is the acrobat. So I showed you this one at the end last time, right? So this is like your double pendulum, where you have 2 joints and only an actuator on the elbow, right? And a passive shoulder joint. And the goal is to kind of swing it up, similar sort of deal. These two are both like some of the most classic benchmark problems in like robotic motion planning, optimal control, et cetera, right? Total classics. So let's do this one. Same kind of deal. We have a package for giving us this, RK4, same derivative stuff as before. 10-second horizon, random cost weights that I made up, not interesting. Blah, blah, blah. Okay, same stuff as last time. I'm going to do the same thing. We're going to do backward pass. I've got both the Gauss-Newton and full Newton. We'll do Gauss-Newton first. That's sort of the baseline. Let's see what happens. So I'm going to comment out those second derivatives and all this stuff. Regularization stuff's in there, which you need in general on the full version. We're going to start this out just hanging down with some random noise on the U's. This is for later. We'll do something fun. So that's the idea. Hanging down, a little bit of noise, again for like symmetry breaking purposes. If you start getting into this stuff, you'll find you want to try to be a little bit clever about how you initialize these things. And it's often a good idea to not use like all zeros, for example. It's often better to either do something a little bit smart or put in random noise, like small white noise is usually a better choice. So that's what's going on there. Initial rollout, blah, blah, blah. So here's the same thing as we just looked at. I don't think there's anything different in this code. It's the same code. And let's see. 300 or so iterations. That's what the cost is. That's what the state looks like. That's what the controls look like. Let's watch the video animation-y thing. Okay, so yeah, zoom in a little bit. So it's doing this sort of like single pump kind of thing, right? So it's sort of pumping once, twice, and then swinging up. And that's sort of, we're effectively minimizing control torque in the cost, right? So and if I play with the cost function and weight it a little bit differently, you'll get, different numbers of pumps basically to swing up, right? So if I like, for example, put a bigger cost on you and like maybe a less cost on the states, it might take more pumps, which would be, less torque to get it to the top, right? So you can play games like this. Kind of cool. Okay, so now we're gonna remember these numbers. So like 300 iterations, 562, whatever. We're gonna go do the full Newton version and look at that. So I'm gonna try these guys. Comment. Cool. And what's going on? Same stuff. It's going to take a while. So in particular, last time, right, it was definitely fewer iterations, even though it took longer. You'll see in this particular situation, it's probably going to take more iterations. Yeah, so 960 versus 300. So this is to say that I could probably do better than that if I dialed in in particular, the regularization. Here, what is ending up happening is it's regularizing a lot, and that's perturbing the Newton step a lot. So I'm not getting great Newton steps. And it ends up doing like strictly worse here. It's like way more, it's 3x the number of iterations, right? So this is to say that like whether or not it wins in terms of iteration count is also very dependent on the problem and very dependent on your implementation being good. In particular, your regularization strategy needs to be good for it to actually win and for you not to just like waste a lot on your regularization. So, but yeah, comes out with this exact same solution once again, right? So kind of cool, whatever, this double pump thing. Here's the last thing I want to do, which is kind of fun. So I'm initializing this up here with like random white noise, just like a little bit of white noise. I'm gonna actually, I did this a bunch last night, and you'll find, well, I'm gonna uncomment. This is just a saved initial guess from when I was doing this last night. And this happens every, I don't know, like 5 or 10 times you try this with random inputs, you'll find the following thing happening. So let's do this. We'll just run one more time. Wait for this thing to converge. Be about the same as last time because I'm doing the full Newton thing. Okay. Okay, so that was a little better, 600 something. Look at this though. Look what happened to the trajectory. This is a quite different trajectory, right? So what's going on here? Let's watch the video. So this has like, oh, it's a different trajectory with like a weirder pump behavior. What happened? Why did I get a different answer? That's exactly right. So I'm initializing this with random noise. It's a non-convex problem. There are potentially multiple local optima. So notice like the cost that this converged to is almost the same, right? It was 562 point something, about 563. This has almost the exact same objective value, almost the exact same cost, but it's a like qualitatively very different looking trajectory, right? So what this is telling you, there are multiple local optima here, and which one you land in is purely, based on your initial guess. So you can end up, yeah.
The local optima are not always going to be like close in their cost, though, right?
No, yeah, in general, not at all. It's total crapshoot. There's like basically nothing you can do to control this. It's just like fact of life when you're doing like nonlinear, non-convex optimization. There are going to be multiple solutions like local optima. You don't get to pick which one you land in. It's totally dependent on the initial guess. Here we're using like random initial guesses. So if I run this 10 times, potentially I could land in different local optima every time. So fun fact, I don't know, something to keep an eye out for sure. And the cost could be wildly different. You could find yourself in bad local optima where the cost's a lot higher than you might like. And there might be, much better ones. There could be a bunch of them nearby each other, right? You can even get into situations where there are continua of local optima, where you have like a subspace of local optima that you can like sort of move around in. Lots of solutions. There's like a continuum of them. So all of these are possibilities. Yeah.
Practically, what do you do to try and mitigate this? Do you try a bunch of different starts and see which one ends the best? Are there other things you can do?
Yeah, so it depends. Like in a lot of situations, like we don't even care, right? So in a lot of robotics problems, we just care about getting to the goal and not looking stupid. So often like the cost functions we write down are kind of just made up nonsense that don't really matter. So being like globally optimum, like I just made up that quadratic cost function, right? It's just completely made up. It doesn't matter if I hit that optimum or not, right? Like all I care about is obeying the dynamics, not like violating constraints like torque limits and like getting to where I want it to go. Do I really care if it looks like this or the first one I found? Practically, probably not, right? So in a lot of cases, you just don't care. And like just finding a local optimal solution is good enough for most applications. There's actually like historical examples from back in the day where people like found solutions to these problems that like they published and stuff to random problems that ended up being like extremely suboptimal local optima that they found. And like later people were like, oh yeah, there's like a solution that's like 5x better than this, but like that became known and popular and whatever. And stuff like this, right? So these problems are hard in general, and just finding any solution is usually good enough for our purposes. If you're in a situation where you really care, then there are lots of things you can do. Lots of random restarts is a good idea. There's often like heuristics you can use. But once you like go down the path of trying to find better local optima, and like this turns into a global search or global non-convex optimization situation, which is NP hard. Like you just can't do it without like exhaustive search basically. And it's a hopeless sort of thing to try usually. So it's usually not a good idea to even attempt that. And usually you'll like try this a few times, come up with something that looks good enough and just be happy with it practically. Yeah. Did you have something?
Yeah, I mean, I just want to ask if the amount of complexity of the problem just comes from the dynamic.
Yeah, in this case, yes. Here we defined a convex quadratic objective, right? So the cost function is nice. And usually you want to do that, right? Like I get to make that thing up. And like we just said, I usually don't really care about the cost function that much. It's usually just designed to like come up with something that doesn't look stupid. And I can kind of tune it and play with it a bit, right? But like usually it's a good idea to just make that simple and nice and convex. Because we usually don't really care about the details. In some other applications, you might really care, but in our sort of like robotic motion planning applications, it's usually like some energy term, some tracking term, whatever, and it's not a big deal. Yeah, the dynamics you can't help though. That's physics. You got to obey the physics, right? So you have to live with that, and that's nonlinear and therefore hard. These are facts of life. Anybody else? Yeah.
So with the regularization, rather than like adding in this term to like try to push it towards a positive semi-definite, could you subtract out the like the DDP term or the tensor term?
Yeah, you absolutely could. Yeah. So like maybe a smarter way to do this is to just check and then say, oh, if this is bad, maybe I won't even bother with the tensor terms on this iteration. Maybe I'll just do Gauss-Newton and then try again next time. And in general, like early on in the solve process, when you're far away from the optimum, that's probably just the right move. So generally speaking, the faster convergence of like the full Newton with those extra terms doesn't kick in until you're really close to the optimum. And then the other kind of practical thing is usually, just like we don't really care about being globally optimal, we usually don't care in most robotics applications about being super close to the local optimum either. Like getting it in the ballpark and being accurate to like a couple decimal places is usually good enough because our models aren't that good. And again, we usually just care about the robot not face planting and looking stupid. So as long as it gets there and looks decent, like cool. So achieving super tight tolerances is also not a thing we usually care about. And therefore, again, once again, Gauss-Newton, totally fine for getting you 2 or 3 decimal places. That fast tail convergence that you get from the full Newton stuff, we don't even really care about either. Like here, I'm doing this to 1e-2, which is super coarse, right? So here, it's not going to make a big difference either. Cool. Any other questions? So local optima, regularizing. I think that was all I wanted to talk about here. We good? All right. More notes and stuff. Let's go talk about some.
Sorry, I have another question.
Yeah, sure.
So could you force it to take like multiple swings? Like,
Yeah.
Are there ways to like actually say like I want it to take 5 swings?
Yeah, absolutely. So like saying, so from here, if I wanted to play around and do that kind of thing, what I'd probably do here is stretch the horizon out a little bit and then put a higher cost on the use. And that would say like use less torque, right? Which will make it take lots of swings probably. And then we're going to do that in a little bit in a slightly different way. But yeah, so basically from here, if you want to engineer the behavior to get it to do weirder different things, that's cost shaping, right? So you go in, start playing with the cost functions, maybe start playing with initial guesses to get yourself into different local optima, right? But generally speaking, it's just a game of like cost shaping to get the behaviors you want. And yeah, you can get this probably to do like weirdo many pump things and stuff like that. All right, cool. That's that. Okay, so back to the notes. Some things to say about these things. Let's see. So we got cart pull and acrobat, swing up. Basically, take away things. DDP can converge in fewer iterations. But the iterations are more expensive. And then just in terms like ILQR often wins in wall clock time, and is what you'll see 90+% of the time in practice. Cool. And then the other note that we just saw was that in general, these problems are non-convex. So there are multiple local optima that you can end up in. And it's just something to be aware of. And I would say generally, just don't stress out about that too much. Usually isn't a big deal. And this is also all of machine learning is non-convex and with lots of local optima in it. We still do it and it still works. So seems okay. Okay, so stuff to talk about then. Let's talk about regularization really quick. So I had to do it in those DDP examples, right? And you saw that where it kicked into the regularization stuff. So some notes on that. So just like standard Newton, you can have, right, our V and or sort of action value. These guys can become, these Hessians can become non-positive definite, or and we don't like that. So we want to keep, and to keep things going downhill in the descent direction, we've got to regularize, right? So other comments we saw, it's definitely necessary with the full DDP. And in fact, like how exactly you regularize can have a huge performance impact, and means that like actually winning with DDP really means you got to dial that in pretty well. And then also though, it's often a good idea with ILQR as well in more complicated settings where you potentially can have ill conditioning and round off errors drive your Hessians indefinite numerically. We'll talk about that. So there are lots of ways to do it in this context. So in standard Newton, right, it was cut and dry. You like pad the Hessian, with the multiple V identity. Here, it's less obvious what to do. There's a few different things you can do and that you'll probably see in practice. So here we go. So the first most obvious thing is you can just add a multiple of the identity to the cost Hessian, just like standard Newton, right? We usually don't do that here, though. Usually we do some other things. So one thing that we see a lot is you can regularize the P's, the capital P cost to go Hessians as needed in the backward pass. So you can like basically check the cost to go Hessians or action value Hessians on the way back. Actually, we should say both of those, right? So the P's, or what I did, so you can regularize the P's or the G's, like the cost to go Hessian or the action value Hessians, right? Kind of check them at each time step, and if they're not positive definite, regularize them until they are at each time step kind of individually. So that's what I did in the examples I showed you. That's a pretty common way to go. Another option is you can just regularize. So those will work on sort of in all cases. You can also think about just regularizing the GUU block. So just the one block of that action value Hessian. So this sort of thing. Why is that a good idea? Or why not? Any thoughts on that? Okay, so the reason you might do that is that that is the only block that you have to invert in the Riccati equation. So I'll write that down. So remember when I solve for the K's and the D's, I end up doing D is GUU inverse little GU, and K is GUU inverse GUX. So strictly speaking, like to solve for the control updates, the only matrix I have to actually make sure is invertible is that GUU. So this one is a good choice. And this one's super common in ILQR implementations, because there things are supposed to stay at least positive semi-definite on their own without needing regularization. But due to small numerical round-off-y kind of things, you can end up with an ill-conditioned situation. And so if things are ill-conditioned, you want to make sure when you solve the linear systems, you're regularizing a little bit to help with ill-conditioning. So this helps you with that, where just when you try to solve these linear systems, aka invert the matrix, you can help the conditioning by padding that block a little bit, but it's not going to fix any indefiniteness in the cost to go Hessian in general, right? So this is a good one for just helping with numerical round off things in ILQR, but not for really bad, truly indefinite things that happen in the full DDP. Okay, let's see. And then the last comment is, strictly speaking, you shouldn't need regularization for ILQR, but often in practice you do because of floating point round off stuff. Okay, so that's the regularization story. Any questions, comments, thoughts about any of that stuff? These are sort of like practical tips and tricks. Okay, so then sort of some like summary DDP notes. Sort of pros and cons, if you like, because we're going to kind of move into some other methods next. And so the kind of the good stuff, DDP is known for being extremely fast in general. It's one of the fastest trajectory optimization algorithms out there, both in terms of iterations and wall clock time. So if you write a good implementation, it can be really good. And often these are the methods of choice for online real-time applications for that reason. And for one more reason we'll talk about in a sec. Okay, yeah, so it's very efficient. it's really kind of the key reason why it's efficient is because it's exploiting that like dynamic programming structure, right? Sort of approximate dynamic programming kind of thing. Let's see, other cool things about this. This can go either way though. It is what we would call anytime dynamically feasible. What I mean by that is it always obeys the dynamics, because at each iteration of the algorithm, we always do a forward rollout, right? So by construction, every single iteration of one of these methods always obeys the dynamics. What that means is you can stop the solver early before it's converged to an optimum, and you can still run that trajectory. It'll still work on the robot. So even if it's suboptimal, it still obeys physics, and it's still a perfectly like feasible trajectory that you can execute on hardware. So it's yet another reason why it's a good, kind of maybe good method for real-time stuff. Okay, another cool thing about this that we kind of mentioned in passing, but I haven't really dug into and didn't do any examples yet, is that you get a TV LQR tracking controller for free. So we talked about how the backward pass of LQR and DDP, the Ks you're getting there, and like most of that backward pass thing is the same exact Riccati equation as LQR. So at convergence, so what happens at convergence of this algorithm? Remember, we have like in the backward pass, we compute these feed forward Ds and feedback Ks. At convergence, the Ds go to 0, and you're left with just the Ks, right? Turns out at convergence there of one of these methods, the Ks are the exact same Ks you would get from an LQR tracking controller. So not only do you get an open loop trajectory out of one of these methods at convergence, you also get for free a time varying LQR tracking controller. And this is sort of thinking about this more deeply. It's actually kind of tells you one of the like deep reasons why LQR is so good. We kind of talked about before, right? How LQR is really hard to beat in practice, and it's sort of super good, and generally the first thing you should try. One of the reasons for that is what we're doing here, remember, right? These DDP things, it's approximate dynamic programming. We're doing dynamic programming using like a second order Taylor approximation. And what LQR is, if you think about it, it is the local first order Taylor approximation of the optimal feedback policy. So if you can imagine, like if I had magic infinite compute and I could solve the full dynamic programming problem and find the globally optimal feedback policy, the LQR policy would be the local small deviation a version of that. So for small deviations, LQR is the optimal thing, is as good as the fully optimal dynamic programming solution. So that's kind of like a I don't know, cool deep result that's like LQR is good, and you get that for free out of these things. And so all of these are to say this stuff can be very good for online stuff, where it's fast, comes with the tracking controller for free, dynamically feasible, all that good stuff. Okay, some cons now, like why might you not want to do this? Yeah.
So how's the tracking controller? So I remember for LQR, it was like a stationary point.
So there's two versions. There's the sort of time invariant, which is a set point, and then there's time varying LQR, which is for tracking a trajectory. And so the K matrices that you get out of DDP or LQR at convergence are the exact same K matrices you would get from a TV LQR tracking controller. Yep.
Can you give an example where before convergence, the trajectory directly what you get would not be dynamically feasible? Like here you mentioned that it's always dynamic.
Yeah.
So in cases where we do like a backward pass first, in those cases, would it be before conversion?
So because you're always doing forward rollouts, anything that comes out of a forward rollout here is going to be dynamically feasible. So any of these algorithms will give you anytime dynamic feasibility. Algorithms that are based on collocation and like direct transcription, which we're going to talk about next, they work a little differently. They do not have an explicit forward rollout. They only obey the dynamics constraints at convergence. So intermediate iterations, if you stop early, don't obey the physics. And that could be a problem. So that's what we're talking about. That's the contrast here. So anything like ILQR DDP always has this rollout and always has the dynamic feasibility property, which is sometimes good. It's bad for other reasons that we'll talk about later. So in particular, okay, so here's some negatives about these methods that we just talked about, and we'll get more into this. They do not natively handle constraints. So we just kind of talked about, like these methods only really address that unconstrained trade-off problem I wrote down before, where it's just dynamics and cost function. If you have torque limits, if you have obstacles, stuff like that, that's going to break these algorithms. It doesn't fit. You have to do some hacky stuff to sort of smush those in. People do lots of hacky things. We're going to talk about it in a sec. But constraints are not necessarily a great thing here. The other thing that's the other side of this anytime dynamic feasibility thing is that these methods don't natively support what's called an infeasible start or infeasible initial guess. So what that means is I can't just make up a random state trajectory as a guess that doesn't obey physics, which you can do with the other methods, these collocation methods. You can make up a random, like, made up state trajectory that doesn't obey the dynamics and kick the solver off with that as a guess. That can be super powerful, actually. Like if you have a sample-based planner or some heuristic for generating guess trajectories that are just kinematically feasible, say, that don't obey physics, you can use those in a collocation method, and they might be really close to the right answer, right? You can't do that here, which can be a huge disadvantage sometimes. These are particularly bad for like maze or bug trap problems. So problems where you have like complicated, obstacle situations. These can fail at and have a really hard time. And then the last one is that these methods, they're basically like, kind of very similar-ish to like backprop, and sort of similar to those methods. They can suffer from numerical ill conditioning if you have really long horizons, really long trajectories, because you're doing backprop it's like having backprop through a very deep neural network, right? You have lots and lots of stages, and any kind of round off truncation stuff and ill conditioning stuff is going to accumulate as you go. So you can end up with what is in machine learning called the vanishing gradient or exploding gradient problem. In control, it's often called the tail wagging the dog problem. You could basically get like compounding numerical badness as the trajectories get longer, and that can eventually get you and become a problem. And yeah, there are ways to deal with that, but that's a thing. Okay, cool. Any questions about any of this stuff? And some of these, yeah.
What kind of problems can DDP not solve?
A lot of problems.
Uh,
It can't solve any problem except for the one that I wrote down at the beginning of class. That's the only one it works on, right? So I mean, like, not to be super, like, I don't know, flippant, but it's basically like, yeah, the common, motion planning type problems that you would like to solve that it doesn't necessarily handle out of the box, or things involving torque limits, constraints, keep outs, obstacles, safety constraints, that kind of stuff. And there are lots of scenarios where this will break. It only handles that like pure cost dynamic sort of setup with appropriate smoothness and all the other conditions we talked about. Okay, so let's talk about some extensions then. The first one that's worth talking about is how to handle constraints in this DDP setup. What are the standard hacks that people do, which are very common? And some are better than others, and some of them are really bad, and I don't know. It's worth talking through some of these. Some of, you might see these, you might be tempted to do these things. You probably shouldn't. Here's some thoughts on this. Many options. Depending on like the type of constraint. So the first one that shows up all the time in robotics are torque limits or thrust limits, like actuator limits. Those are fairly easy to handle, and there's lots of ways to do it. The first thing you'll probably see that's super hacky but can work is a so-called squashing function. Let's write that down. The most common one of these is like tanh. And how this looks is you take the actual U that you're solving for, and you run it through a tanh function before it goes into the dynamics. So you basically like nest the tanh sort of with the dynamics. And the idea is this thing saturates, right? So you can set up the tanh so that it saturates out at your sort of U max and U min. So you do something like this, right? So this would be the U on the input, and this would be this like U tilde that's gone through the squashing function, and you'll have something like U tilde equals U max times tanh of U over U max. That makes sense to everybody? So like when you're near the origin, well within the limits, the tanh is approximately linear. So what goes in comes out, and then as you get towards saturation, as you get towards the torque limits, the function is going to saturate out, and as U goes to infinity, U tilde just goes to the U max value, right? So this works. It's effective, but it adds a big nonlinearity into the dynamics, which can make the algorithm take more iterations to converge. So I don't know.
A quick question.
Yeah.
Why are you dividing by Umax inside the 10H?
Because I'm normalizing it so that it saturates at Umax. That make sense?
Okay. Yeah.
Does that make sense to everybody else here? Yes. So like, I don't know. We could talk offline about that if that doesn't make sense to you. Okay, so that's one option. Not the best option. A better option is, these are simple box constraints, right? If you remember, when we do the backward pass of this thing, at each step in the backward pass, we're solving a QP basically, right? We're minimizing that quadratic cost to go or action value approximation. So why not just, we're at each step, we're minimizing that quadratic function with respect to U. Why not just throw some torque limits on there and solve a box constrained QP? So I can do that. I can actually just, instead of that unconstrained solve, I can solve a constrained QP at each time step going backwards with the explicit constraints in there. So that's sometimes called control limited DDP. So when I solve for delta U, it's going to be argmin over delta U of my action value thing. And that's what I'm doing right now, right? And it has a closed form solution. I can just tack on these constraints now. This should be U plus delta U in here. Cool. There's some more details there, but like that's the basic idea. If you're into that, there's a paper from Emo Todorov's group from like, I don't know, 6 or 7 years ago that does this. Happy to share. Okay, so that's for input constraints. Those are pretty easy. You can handle them in these kind of easy ways. State constraints are a little harder.
A question on this
Yep.
one. So like we can have box constraint on the U if we're having this constraint in the backward pass. So we can also have whatever other linear constraint on the U here.
Yeah, any U constraints are pretty easy to deal with, like this. Yep.
Okay, cool. Thank you.
Yep. Okay, so state constraints. State constraints you'll often see done with penalties. So you just throw a penalty in the cost function that penalizes state constraint violations. This is, fine if you only care about very coarse tolerances, but in general, it's going to lead to ill conditioning, and it's going to take, huge, really stiff penalties to get good constraint tolerances. So if you're satisfied with really coarse tolerances, maybe this is okay. A better option here is, like we talked about when we did general optimization, I can add a quadratic penalty to this thing really easily. I can also wrap the entire DDP algorithm in an augmented Lagrangian method. Remember, in the augmented Lagrangian method, we have quadratic penalties that fit super nicely into our quadratic action value thing. And I have a Lagrange multiplier term, which is a linear term, right? So linear plus quadratic, that's exactly what I've got in my action value approximation and cost to go approximation. So it like fits in perfectly, and it makes it kind of very naturally work. So this is in fact what our lab's kind of fast custom solver does. And I'll show you some of that. So the AL method, like I just said, adds linear, AKA Lagrange multiplier, and quadratic, AKA penalty terms to the cost. So this is like a super easy fit. I.e. you can handle that exactly in the DDP method, right? You don't have to Taylor approximate it. So that's kind of cool. And I'll show you some stuff. This is basically like very effective for fast convergence. To like coarse constraint tolerances. Which is what we usually care about in real robotic control applications, right? Like as we were kind of just saying, but can break down if you try to push towards really tight tolerances. If you have any questions about this idea, talk to your TA, Brian, who is the lead developer of our solver. Yeah.
When you say this breakdown, does it just mean it takes too many iterations to converge? I thought Lagrangian did a much better job at handling type constraints than just penalty.
It does, yeah. So it's absolutely unequivocally better than the penalty method. But basically, like the penalty stuff is going to make the conditioning strictly worse, right, than like an unconstrained problem. And these DDP/ILQR methods already have some conditioning issues due to the long trajectories, especially because of the sort of backproppy, backward pass stuff. Strictly speaking, that Riccati backward recursion is numerically unstable. So that means like error accumulation due to floating point round off and stuff just gets worse and worse and worse as you go backward farther. So it's already kind of has some issues with this. So we're making it worse by adding these penalty terms. And yeah, augmented Lagrangian is definitely better than the penalty method. But if you have a really long trajectory and you try to crank towards like really tight constraint tolerances, you're going to have problems basically. So we have some tricks for dealing with this in our stuff. It's kind of beyond the scope of this discussion, but like there are ways to deal with it, but it's sort of requires fancier tricks and it's not trivial. I don't know if that was unsatisfying, but yeah, we can talk more after if you care. Okay, any other questions about this? Okay, there's some, should we go into this? Yeah, there's a few other little things. So there's some other things that are worth like just mentioning real quick. So what if we want to have a free initial state? What if like instead of a like X naught given, what if we have like, what if we can pick our X naught or something like that, right? Which is not an uncommon thing. Or the other version of this that shows up is what if you actually have like parameters in addition to the controls you want to optimize? Like what if you're doing like design optimization? Like what if you could pick the leg lengths of your robot, or you have other design parameters you want to co-optimize? All kinds of things you could imagine doing there, right? So if you want to do that, there's sort of some tricks. Those all look basically the same as this, by the way. So anytime you want to have like some additional handful of system parameters in addition to the controls, you can sort of tack those on as a sort of fake sort of like U naught that shows up before the initial time step. So you add a fake like k equals 0 step. That look like this. Where this is going to be like 0, and this is going to be an identity. And now U naught becomes x1. And you can basically, throw anything you want in there, actually. So you can throw like literally any problem parameters, system parameters, et cetera, in this, and you can like optimize those along with the trajectory, which can be useful, can be kind of cool. The last one to mention is this like free final time kind of stuff.
Quick question on that.
Yeah.
Does this only work when X and U are the same dimension? Like otherwise, what do you
Yeah,
do?
you can actually, so there's nothing in here that says the dimension of U can't change. So actually you can like stuff a whole bunch of extra things into U1 that aren't in the other U's. Like the dimension of U does not have to stay constant along the trajectory, which is kind of interesting.
Okay, yeah, then it makes sense.
Yeah.
Is there some sort of like Markov assumption where like the previous state can only, or the next
Yeah.
state can only depend on the previous state?
Yes.
So like, how do you get a U naught to affect, like parameters that U naught to affect?
They only affect the next state
Okay,
and the
so
state
you-
after that. Yeah. So there's a sequential and time thing, right? So if you want to optimize some other weirdo parameter, it has to go in at U naught, because then it can affect the whole rest of the trajectory, right? So like basically what you do is take it and then bury it in the dynamics model from then on, right? So it can be anything you want. Any other parameters that you care about, you can throw in there. Yeah.
So what you're doing here is like trying to take an initial condition that optimizes the problem also.
Yeah.
So why doesn't it just say the initial conditions is what you're like? That makes sense.
I don't know exactly what you're getting at there.
Like, if you're trying to get to a specific position, why does it say the optimal solution is to start at that position?
So, I mean, I'm not saying start it. So if I want to just start at some initial state, cool, done. This is like, I don't care about starting at some exact initial state. Maybe I have some other parameters, like maybe I can start anywhere within some bounded region is legal. Also, it can be things like optimize some other system parameters other than the state, like parameters of the model, right? Like could be design parameters of the robot, how much fuel you should carry, like, I don't know, what masses, inertias, like all kinds of weird things that you can imagine, like literally anything you want. Anything you want to optimize in addition to the control trajectory, you can stuff into this U naught term and optimize. Yeah, cool. Anybody else?
Are there bad problems with having to push gradients all the way back through your whole trajectory?
Oh, yeah.
to hit these?
Absolutely. Yeah, the same problems we always have. It's the same tail wagging the dog, sort of problem. So it's not any worse than like U1 would be. Right.
These parameters might have a bigger effect on the whole problem.
They might, yeah. So yeah, you can get like ill conditioning. Absolutely. Yep. It can happen. Yeah. So this is always a problem though. Like there's this sort of thing always shows up. It's always something you have to like kind of finesse a little bit and worry about a little bit. There's all kinds of fun games you can play with that trick though. We have some games like this where we like, for example, bury a neural network inside the dynamics to do cool things. And then you can optimize the neural network weights like this, right? It's kind of cool. Okay, so last thing. And I can't write, or should we just call it? Yeah, we got 1 minute left. So, okay, we'll skip this. Maybe I'll do it next time. But the last thing I'll show you then is fun code again before I send you on your way. So here's a cart pull part 2. So we're gonna do this. This time everything's the same, 5 seconds, whatever, same cost function, blah, blah, blah. Now we're going to do it with constraints using our lab's custom solver that Brian mostly developed called Altro, which stands for Augmented Lagrangian Trajectory Optimizer, which is DDP or ILQR wrapped in an augmented Lagrangian method with a whole bunch of fancy tricks to make it go fast and stuff. So here's what we're going to do. Everything, this is all the same, but I'm adding in. So if we go back and look here, I did like a 1 pump swing up on this guy, but look what the controls did. This was like, minus 20 plus, I don't know, 10-ish. I'm going to bound the controls at 3 plus minus 3. So way tighter than what I had before. And in particular, it's so tight that I can't do a 1 pump swing up. So it's going to force it to do lots of pumps to get up. So let's look at this. Blah, 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 solver stuff. So you can see, I don't know, 97 iterations, 20 milliseconds to solve. So this is what a good implementation looks like. I solved this problem from scratch in 20 milliseconds, right? So you can do this stuff online. Let's watch it. So yeah, you can see it's like way less control authority. So it has to do this like many pump thing. Here's what the controls look like for that. So you can see it's basically railing right at the torque when it's, back and forth. This is what we classically call like a bang bang control policy, right? Where it's hitting the torque limits repeatedly. Anyway, that's it.